Okay, so here's where we were last time. We were talking about integrals. So this is we're going to generalize the idea of single variable integrals. And so the first thing we did is we spent a little time talking about what are single variable integrals, and I think it's very important to note that they are Riemann sums, right? They're not some formula that is very convenient to compute with. That's a theorem, not a definition. They are not area under the graph, right? That's an application, not a definition. So the definition, so ultimately what an integral is, Riemann sum. So that's what we're going to generalize. So we generalize that by noticing that, roughly speaking, this construction does sort of a four-step process, right? So the domain gets chopped up into little pieces. On each little piece, you multiply some function times the size of the piece. Now, what that function is depends on the application, right? So, that we can't be specific about that. You add all those up and take a limit to get those round-off errors to go away, and that gives you this Riemann sum construction. So we're going to take these 4 steps and apply them to the broader setting of now a 2-dimensional domain. And so this is where we proceeded. There's our 2-dimensional domain. You can see we chopped it up, right? And blah, blah, blah. And here's our definition of a double integral. Okay. Now, why would we want to do such a thing? Right? This is a generalization of something that's proved itself useful, but is this useful? Well, yeah, it turns out that it is. Here's lots of various applications. You can compute the volume under a graph with a double integral. Right? You can compute the amount of mass in a sheet where the density is distributed in whatever way. Right? Some arbitrarily distributed mass across a 2-dimensional region. Double integral will add that up for you. You can compute the population in rectangular shaped region, again, with a double integral. Notice that in all of these cases, what your integrand is depends on the application. It's not always the same thing. So you got to pay careful attention. What should your integrand be? And in all cases, it boils down to what is the thing that you would multiply by size to get whatever stuff it is you're interested in computing in the first place. Right, so typically it's a density of some sort. For example, this is known as population density. Right? This is mass density, etc. Okay. All right, how do you compute these things now that we've seen how applicable they are, widely in various different ways? How do you compute them? This is an intuitive argument. This is not intended to be rigorous, but I think it's pretty persuasive that the volume computation that we just argued could be done with a double integral. You can see with this 2-step process can also be computed with an iterated integral, we called it. Right? So if these are 2 different ways of computing the same thing, then wouldn't you expect that they'd be equal to each other? And again, the fact that this computes volume, that's one of many nice applications, but the fact that we can compute double integrals is really the more interesting fact. Because double integrals connect to so many other different things. And so this is our sort of final punchline then. 3-step process for how to use double integrals to compute things. Step 1, recognize, however it is, that the application you're interested in can be expressed with a Riemann sum as a double integral. That's the first step. Second step, rewrite your double integral as an iterated integral. And third step, crank on that iterated integral. So you have to apply the fundamental theorem of calculus, and then you have to apply the fundamental theorem of calculus again. But that will get you down to a number answer. Okay, so we need both of these ideas. We need the concept of an iterated integral so that we can apply the fundamental theorem of calculus. At this stage, we don't really have a 2-dimensional version of the fundamental theorem of calculus. We just have the single variable, Math 111L fundamental theorem of calculus. But we also need 2-index Riemann sums or double integrals so that it'll connect to applications. Right? It doesn't make any sense in most cases to to go straight to that? It's just, it's not clear, what that argument would be. Why is it that the amount of work that it takes to whatever that would be a single variable integral of a single variable integral? That immediate connection is not there. So both of these notions, iterated integrals and double integrals, both really important. So make sure you show that when you do these calculations. Make sure you show the double integral, right? And then, of course, it's going to be hard to not show the iterated integral, because that's what you're going to be applying the fundamental theorem to. Okay, so that's where we left off last time. We're going to just proceed along, and I asked the next question, very reasonable question. What if you're interested in computing a population of something other than Wyoming or Colorado? Right? What if you want to compute the mass of something that's other than a rectangle? What if you have some application where the domain just isn't a rectangle? Okay, so for example, maybe our domain is this, and let's say a couple of quick words about why. For example, might I be interested in a double integral on a non-rectangular domain? Well, maybe this is a particular state of which I want to compute population. The strategy would still apply. I can't multiply population density times the whole area because the density is not a constant. But on each little piece, if I slice it up to itty-bitty little pieces, density times area gives you population, and you end up. The whole argument makes sense, right? So that'd be a good reason to want to do that. And every other application we've looked at, you could still apply. So for example, maybe we'll want to compute, I'm going to put a z-axis on here just for visualization purposes, and maybe there's some surface up here. Let's see if I can. Okay, I'm going to cheat to draw what I want to draw here. Forgive me for cheating. That. There we go. Okay, so maybe there's some surface up here that I have in purple, and I want to compute the volume under that surface, sitting over this weird, lumpy-looking shape D. Right? Could happen. All right, so how would I go about computing? And I'm going to start with this volume example just because it's easier to visualize what's going on. Now keep in mind the way we compute volumes with iterated integrals is to, we know how to do it with double integrals. There you go. There's double integral. To do it with iterated integrals, I would take slices like that and multiply the area of that slice times the thickness in the x direction, right, and add up all those little volumes. Okay, so let me say that a little bit differently. Oh man, I didn't mean to erase that. Let's see if I can. There we go. So said differently, we would be taking slices of area and integrating across that way. And then you eventually realize, okay, well, sure, I know what my integrand is going to be. My integrand is going to be the same as the integrand for the double integral, just like it was. The shape of the domain doesn't have anything to do with that fact. All that I'm really interested in keeping track of at this point is what are the range of values of these variables, x and y, as I do those appropriate integrals. And in order to keep track of the range of values, notice you don't need the z-axis, right? What's happening with x? Who cares how high you are? Who cares what z is if all you're interested in is x and y? Right? So the nice thing about it is that even though you might visualize this three-dimensional slicing process like we did back here, if all you're interested in is the range of values of x and y, don't bother drawing the whole three-dimensional thing. All you need, in fact, let me cheat again for cleanup purposes. There we go. All you need is the two-dimensional region itself. Look at that two-dimensional region. And, well, as x goes from A to B, there's what one of those slices looks like. There's the first slice, thus giving me a starting value of A. There's the last slice, thus giving me an ending value of B. And then you see here the x integral. X goes from A to B. So again, there's a three-dimensional version if you'd like, but it's not necessary for working out the bounds on the integral. Okay. So looking only at this at this picture of the domain, we've got x going from A to B. And now let's think about the inside integral. So for this value of x, we're going to fix that value of x now, just as we did before. And now y goes across like that. Right? There's a first value of y and there's a last value of y. Yep.
Did you arbitrarily pick those points? Would it be like?
Oh yeah. This is just an arbitrary lumpy picture, so I didn't want it to look like a constant.
Right.
My goal with that picture was for it not to be a rectangle.
So I'm saying like when you were picking the limits, would you pick like the min, the max?
There's a bunch to talk about there, and that's what we're gonna get to. Yeah, totally. It's great. It's exactly the next thing you want to be thinking about. Yep. Okay. Right. So we're going across this slice, right? For a given value of x, and again, if you want to think about it as, this, what I've really got there is some area, and this in here is a of x, per the old argument that I made, right? But I know that a of x is an integral. I know it's an integral dy because I'm clearly going in the y direction. All that remains to be seen is, what are these bounds? Okay, so what are those bounds anyway? Here's the idea. If I want to know what this lower bound is, right, y1, that corresponds to that point that you can see right there. Now, what do I know about that point? Well, I know two things about that point. On the one hand, it's on this curve that I have in green. Right, and the other is, I know what x is. Right, so this curve is going to have some equation, and on that equation, given some value of x, I need to solve for the corresponding value of y. So this is always going to boil down to is the bound that you're interested in corresponds to a point. The point will be on a certain curve. The curve will have some equation. In this case, we don't have an equation, but in context, you'll have an equation, and in that equation, you need to solve for the variable you're interested in terms of the variable that you've already set. Okay. Likewise for the upper bound. How would I find this upper bound there? That upper bound, well, that corresponds to that point. That point is on that curve. That curve is going to have some equation, and in that equation you can solve for y. Okay, so we'll see an example in a couple minutes. Now there is another version of this. You'll notice that in this example that I did, we did our x slicing on the outside. Right, you might say first. I'll come back and talk about that terminology in a moment. But we did the x slicing on the outside, and then it's for a given value of x that I wanted to then know the range of values for y. But you could do it the other way. So, for example, let's consider this picture. Maybe I do my y slicing first. Y goes from C to D, as you can see there. And then I would say, okay, fine, for a given value of y, I'll do this in blue. I need to know what these x bounds are. And it's the same process. Just with, the variables playing opposite roles. But if I want to know, let's say, the lower bound, okay, well, this lower bound, this x1 that I want to know corresponds to that point. That point is on this curve. That curve will have some equation. And in that equation, solve for what you're interested in. We're interested in this lower bound value of x. So in the equation for that curve, you're going to want to solve for x as a function of y, of course, because, well, I already, y is a given. for the purposes of this inside interval, y is known. Okay, so same process. Okay, so that's the big idea. Notice how the two different ways that, let me zoom out one little notch here. Here we go. The two different ways that these differentials can appear is, is it dx dy or is it dy dx? And keep in mind the bounds always go with, right? That arrangement, that choice of which order to go in corresponds to, well, which way are you slicing? Are you doing your what you might call your y slicing first, followed by your x slicing, or are you doing it in the other order? Okay. So there's a little bit of terminology I want to talk about before I do an example, and that's this outside versus inside. There's a temptation to say first versus second. Right? So the strong temptation is to say, look, whichever one's on the outside is on the outside because you're doing that slicing first, and whichever one's on the inside, aren't we doing that one second? It would seem. Right, there's temptation to call them first and second. Here's the problem. The problem is when it comes time to actually computing these integrals, how do you evaluate them? Well, the one that's on the inside, you have to do that one first. You have to do the inside integral first because you don't know the integrand for the outside integral yet, right? You have to work from the inside. And then, of course, you have to, only having done that, can you then do that outside integral second. So this terminology, first versus second, is super confusing, right? And I urge you to try to wean yourself off of that. Again, it's very tempting because in your thought process, well, look at what time it is. I'm starting to think about the x integral, and then it was later that I finally got around to thinking about the y integral, and doesn't that mean this one's first and this one's second? It's very, very tempting, but it's the opposite order when it comes to evaluation. So I encourage you to think outside, inside. And certainly be aware that's the terminology I'm going to be using mostly in this class. Okay. Okay, so let's do an example. Alrighty, so we've got a domain here. That domain is bounded by two curves, y equals x squared, and y equals, come here, color change, y equals x plus 2. And so I want to do some double integral over that. Now again, why do I want to do a double integral of this domain? I don't know. Maybe I want to compute the mass of something. Or maybe this is a lake where I know the depth and I want to compute the amount of water. Whatever. Right? But I want to do a double integral over that domain, and I want to know how do I convert that double integral to iterated integral. A good general rule of thumb, by the way, try to avoid slicing through a corner. I'll show you why in a few minutes. For the moment, let me just say it tends to be a good rule. Just try not to slice through corners. Yes?
What do you mean when you slice through corners?
Yeah, so for example, if I did my slicing, if I did the y integral first, and I was doing slices like that, I just sliced through a corner here. It's a corner in the shape of the domain. It tends to be bad, again, for reasons that will become clear in a couple of pages. Yeah. Yep. So we're going to avoid that by slicing the other way. We're going to do our x slicing first. Like that. By the way, there's a temptation to call this y slicing because look, you're slicing parallel to the y-axis. And if not y slices, maybe some students would like to say, well, we're going to slice parallel to the y-axis. I think this is a bad idea. I don't encourage thinking about what are you slicing parallel to. Think about what are you slicing perpendicular to. The reason is because in this slicing process, it's the values of x that are dictating the slices. It's the values of x that you want to know the starting value of and the ending value of. X is what's relevant in this slicing process. Right? So let's call them x slices, or at least at a minimum say x slicing perpendicular to the x-axis. Okay. All right, so having decided to do that, x is going to start there and end there. How do I find those bounds, the starting and ending values of x? So here we go. Right? I want to know, for example, what is this value of x? All right, so here's, again, the usual game. This bound corresponds to that point. That point is on a certain curve. Well, actually, two curves. It's on that curve and that curve. All right, the bound corresponds to a point. The point is on two curves. Those curves have certain equations. And solve for what you want. All right, so I'm interested in finding an x bound. The bound corresponds to a point. The points have certain curves. The curves have certain equations. There was an x bound that I wanted, so with the understanding that these are the two equations I'm working with, solve for x. And how do you solve for x in this case? Well, conveniently, y has to be equal to both that and that. So that's the x equation that I solved. How we doing? Everybody happy? All right, so make sure to remember this process. It's always the same process. Bounds correspond to points. Points correspond to certain geometric shapes, curves in this case. Those geometric shapes have certain equations. There's your algebraic foot in the door. Okay, so I'll let y'all. By the way, make sure that you know how to do this algebra. That you know how to factor the quadratics and stuff like that. Okay. All right. Okay, and notice down here in our eventual integral, we're going to finish this up in a minute, but our outside integral, right, the one that we're slicing first, -1 to 2. Just like we solved for right there. Okay. Okay, now, what about those inner bounds? There, let me zoom back. So for a given value of x, let's say, this x is fixed. And alrighty, then I'm going to go from there to there in my y slice. What are these inner bounds? We want to know? Well, that first bound corresponds to that point. That point is on that curve. That curve has that equation. Solve for what you want. It's always the same process. Bounds correspond to points. Points are on curves. Curves have equations. Now, what am I solving for here? There's a temptation to feel like you have to actually earn something. Right? I've got to do some work. I've got to actually solve for something and to, take a square root of both sides or something. But keep in mind, in this case, look right there, what I'm interested in. I'm looking for a y bound. So I want to solve for y, which is super easy. I didn't even have to earn it. It was staring me right in the face this time. Right? Not that will always happen. It certainly won't. But situations where, in fact, no work is required, it's good news.
So that will always be the intersection between either, for instance, what if these were two planes? Would be
that's a separate story. Separate story, yeah. Right. Every question is. So I'm going to hesitate to answer. Will it always? Almost always, my answer to that question will be no, because if I can't say precisely exactly what we're talking about, then it makes me nervous. So let's just focus on right now. For example, we're doing just double integrals, and so yeah, right. Okay. But the process is always the same. Bounds correspond to points. That's for sure. Points are going to correspond to, they're going to be on certain geometric objects, and we'll take them case by case. And then geometric objects have algebra. Okay. All right, so that bound, that point, that curve, that equation, there you go. It's x squared and c. It shows up right there. And then likewise, the upper bound corresponds to that point. That point's on that curve. That curve has that equation. Solve for y. Again, freebie. Didn't have to actually do any real algebraic work there. And there's that upper bound. Everybody happy with that? Okay. All right. So let's compute the mass inside of this region. This same region. Now we've already gone to the trouble of doing the slicing process. Not having worried about what our application was. That's stage one of the process. We'll deal with that later. Just thinking about how to turn a double integral into an iterated integral on that domain, and we got this as our result. Whatever you want to do a double integral of, boom, here's your iterated integral. Right? And with that in mind, how would I compute the mass in there if this was your density? Well, mass is a double integral, and as we just showed on the previous page, that double integral is this iterated integral of our density, and now it's off to the races. Fundamental theorem of calculus. Okay, now there is one little twist algebraically. It's not that big a deal. The slightly creepy thing is now these bounds are no longer constants. These bounds are functions, right? Or so it appears. It seems a little scary to have functions in your bounds. Flashbacks to Calc 2 when you did the second version of the fundamental theorem of calculus, which is kind of, I don't know, students find that creepy a lot. Right? Good news, no such thing going on here. That's an illusion. X is not a variable. For the purposes of this integral, notice that X is a constant. Right? So it's only for a given fixed value of the X, that being the variable for this outside integral. It's only for a fixed value of that we're interested in this integral here in the first place. So don't forget, for the inside integral, we're going to be treating X as a constant. Certainly in the integrand when we do the antiderivative, right? But also in the bounds. So it's just a constant. It's just a weird-looking constant. So no problem there. So do be careful when you do your antiderivatives. X is a constant, so it integrates easy. Y is the variable, so there you got to play the game, do the rules. Okay. Note also that in your resulting new integrand, x's, which are now the variable, come from two different places. Some of these x's in here come from the integrand, and some of them come from the bounds. Right? So it's just an algebraic observation. It doesn't really affect, it just feels weird, like somehow, are these x's somehow different from those x's? And they're not, they're the same x's. And so, if it starts to feel like, wait a second, are these the same thing? I just wanted to point out that, yeah, same thing. It's not a problem. Okay, here's another example. This is a quick one. Suppose you want to compute the volume under the graph of that function. Between these three lines, now those are three lines you recognize, and it's not hard to persuade yourself that these are those three lines right there. Now you'll notice I did not draw the picture that I want to compute the volume of, because I already know that volumes are double integrals, and I already know that double integrals are computed by iterated integrals, and so we're just going to write down the iterated integral. This is me being a little bit sloppy here in the context of the class, right? On an exam, you have to write down volume equals double integral equals, and then write down the iterated integral. All right. Okay, so how do we do this slicing process? I'm going to start off by doing my X slicing first. Looking at this picture, that point, not hard to persuade yourself that X starts at 0, because at that point, well, that's clearly the origin. This is clearly X is 0. The upper bound, what is the point that corresponds to this upper bound? Is it that point? Is it that point? Is it this point here? It's all of them, right? So you have the freedom to choose which one of these points you would like to be the point that you think of as representative of that upper bound. I'm going to choose that one there just because it's, I don't know, looks the easiest. That is clearly on that curve, and that curve. And with that algebra to work with, we're to find this point, right? With this algebra to work with, keep in mind I'm looking for a bound for x. So within this algebra, I want to solve for x. And because x is what I want to solve for, it's very convenient to... I kind of missed there, didn't I? There we go. Very convenient to just look at that one equation right there. Okay, inner bounds. We're going to fix a value of x. Y now goes from, one point to another point. This bound corresponds to that point. That point is on this that curve that has that equation. Solve for y, which is clearly 0. Right? What is that upper bound for y? Well, that upper bound for y corresponds to that point. That point's on that curve. That curve has that equation. Solve for y. How do I solve for y? Oh, well, I already know what x is. Right? X is a constant. Previously determined. So, general rule of thumb, just something to notice, kind of a pattern to notice in this process. The bounds for the outside integral, those bounds will be visibly constant. Right? The bounds for the next integral, these will be functions of the outside variable. So if y is on the inside, those y bounds will be functions of the outside variable x. Is that cool? Everybody happy? Everybody see how that's going to... So don't be weirded when you're like, oh my god, but how do I solve for y? I don't know. Oh wait, I do know what x is. Okay. You can do it the other way. Y goes from 0 to 1. I think that's pretty easy to see. And then for a given value of y, x goes from y to 1. Let's talk about where that y comes from. That lower bound of y comes because this lower bound comes from that point. That point's on that curve. That curve has that equation. Solve for x. Right, solving for x. Again, you get y. Is it okay that this is that y is there? Yeah, sure. It's the outside variable.
Cutting through a corner, though.
Oh, you mean like because we kind of the very last slice, boom, is a corner right there? Yeah, you're always, well, not always, you're often going to have a corner at the very start or at the very end, and that's actually okay. We'll see why momentarily. But it's the corner is kind of in the middle of your slicing process that ended up being a problem. Yep. Okay, here's another example. Suppose I want to talk about this domain that's bounded between this parabola and this line. Right, so we've got this kind of, I don't know what you call that shape. Anyway, this little shape right here. How are we going to slice this? We have a couple of choices. Let's start off by doing our x slices first. So our x slices will look kind of like this. Yeah. The starting and ending of that slicing process, well, these bounds correspond to these 2 points. Those 2 points, as it turns out, both of them conveniently on exactly the same 2 curves that have exactly the same 2, of course, equations. And to solve for what you're interested in in x. To get these bounds, what are these 2 values of x that satisfy both of these equations? Well, y has to equal to both x squared and 4. Therefore, x squared has to be 4. And therefore, x is plus or minus 2. Everybody happy with that process? Bounds correspond to points. Points are on curves. Curves have equations. Solve. Okay, then for a given value of x, what's the range of values for y? Well, the lower bound, that point's on that curve has this equation. Solve for y. Easily done. The upper bound corresponds to that point. That point's on that curve has that equation. Again, solve for y. Again, easily done. Yep.
How do we know f of x, y is y?
You're wondering where this came from? That was just a given in the question. Yeah, and again, what our motivation is. So let me just remind you, there's three separate steps in these questions. Right. Step one is to turn whatever your application is into a Riemann sum. And I'm kind of ignoring that for the moment because we've seen a few examples, and there's this more challenging topic at the moment of how do I turn double integrals into iterated integrals. So for these applications, I'm just assuming that there's some application. I don't know, maybe I'm computing a volume, maybe I'm computing a mass, whatever. But for whatever reason, I've arrived at a double integral. And I just want to focus on just phase 2 of the process. Yep. Okay. Right. Let's see. Okay, so let's look at the our other options. Let's slice the other way here. So I'm going to slice first perpendicular to the y-axis, like so. Okay, well, my first slice is there. It's not hard to see as that's where y is equal to 0. I mean, I guess if you wanted to play the game, if you really wanted to follow the rules, how would you get from, the lower bound to that being 0? You could say, well, this point that's clearly at the lower bound, I'd note that that's the minimum value of y. Somebody said something along those lines. I've forgotten who it was. In this case, that happens to be true, and you could make that sort of an argument. You could also say, well, by the symmetry of the parabola, it's the point that's in the middle. Right? And of course, y'all know your algebra 2, and you remember that y is equal to x squared. You know where the vertex is. So any of that stuff. Okay, so upper bound. Well, the upper bound, pick any one of these points to represent that last slice. They're all on the curve y equals 4, thus giving you, again, easy to solve for y to give you that upper bound. Okay, but look at what happens on the inner bounds. Right, for a given value of y, y having been chosen, as I go across there now, my first value of x corresponds to that point. That point is on that curve. That curve has this equation, and in there I need to solve for, now wait a second, let's think this through. I need to solve for x. Right? Because I did my y slicing first. So y is fixed, y goes from 0 to 4, and it's for a given value of y that I'm now interested in an integral going that way. X is my variable. I need to know the range of values of x. So in that algebra up here, I actually need to solve for x. You can see, by the way, it's a analogous argument to get the upper bound. Those 2 points are on the same curve, so it's all the same algebra. So you have negative square root of y to positive square root of y. So you got to pay really careful attention to the geometry of the situation and which way you've decided to slice. Sometimes you have to earn it, right? Do a little bit of algebra, solve for the variable you're interested in, and sometimes the variable that you're interested in is just kind of sort of given to you. Right? But the geometry and the choices that you've made about which order you're slicing in tell you which one is which. Yeah.
Do you only slice for the outer?
Do what now?
Do you only do the slicing for the outer?
Well, it's it's a different kind of slicing. I mean, for the outer one, you can see we're visibly slicing up an area. right? But if you remember why it is that what is it that we're doing in this second step in the process? What are we doing as x goes from there to there? Well, if you like, we're computing some cross-sectional area or something. And how do you compute that? It's just a different kind of slicing. It's slicing up just that line, as it were. So it's still a sort of a slicing. Yeah, it's just a different kind of slicing. Okay, so which way should you slice? Should you always do dx dy? Should you always do dy dx? There's no such simple rule, unfortunately. There's a kind of a version. Anyway, I'm going to give you a kind of a rule of thumb, but it is not as simple as one letter of the alphabet should always precede the other letter of the alphabet. Here's my takeaway from what we saw in this situation. By the way, y'all have a preference between these two intervals? Which one do you like better? The top one or the bottom one? Top one, of course, right? Nobody likes square roots. I certainly don't. Give me the top one. Okay, so where did this little micro ugliness come from? This ugliness came from the fact that I had to solve for x in terms of y. Right? I had to think of, how is it that x is a function of y, but I was given y as a function of x. And so that's the asymmetry. Right? The asymmetry is I was given, not that I can't do that, but it's sort of more naturally given that y is a function of x. And so with that in mind, it makes sense to keep y a function of x in the way that you slice. Right? So one way to say this is put your independent variable on the outside. If there is a well-defined independent variable, try to put it on the outside. Of course, sometimes there won't be. You look at this example here. What's the independent variable? Well, y is equal to x, and x is equal to y. Which one is a function of which other one? I don't know. Take your pick. It doesn't really matter here. And notice, these two intervals are sort of comparably convenient. Right? But in situations where it seems to be more so one than the other, keep that in mind. Okay, now let's talk about corners. We're going to go through a similar calculation here, two different alternatives on how to do an integral. Again, don't worry about what the domain is, or what the integrand is. All we're interested in here is the domain. How do I turn a double integral into an iterated integral? That's all I'm really caring about right now. And here I'm doing my y slicing first, which you'll notice allows me to satisfy my rule of don't slice through corners. Right? And look how the integral turns out, no problem. Right? I'll let you guys check the details. No problem. On the other hand, look what happens if I do it the other way. Here we go. When I do my x slicing first, you're going to want to say that that's the process, that's the picture. And then, okay, well then I can just, solve for these bounds. But look what happens if you want to find let's talk about the upper bound here for y. That upper bound for y. Well, that corresponds to, wait a minute. Is it that point? Well, it's that point for these values of x, when x is between 1 and 2. Right? But unfortunately, it's that point, green. It's that point for these values of x between 0 and 1. So there's a temptation to say, x goes from 0 to 2, and then the y bounds are whatever the y bounds are. It doesn't work like that in this situation, right? Now, what made this catastrophe happen? The thing that made that happen is for these blue values of x, the point is on that curve, but for these yellow values of x, that green point is on that yellow curve. It's on two different curves. This green point that dictates where the upper y bound is, that green point jumped from the blue curve to the yellow curve. Now let's just think through now how might that have happened. Well, a point can jump from one curve to another curve where curves intersect, and And when curves intersect, they make corners. That's the idea. So this is the answer to your question from before. Why not slice through corners? Well, because it gives rise to nonsense like this. Yep.
So does it not cause a problem that you would end up evaluating the line at 1 in both of those?
Yeah, I mean, cutting through a corner at the very end is no problem. So the reason why is when you have a corner, that means whatever integral you were working on, you're going to have to stop that one and start a whole new one for the remainder of your duration. But if you're already done, I was done anyway, so it doesn't matter.
So will that not actually work at all?
I'm not sure what you're asking.
Because if you're right in the middle, the upper bound on one of those is 1, and the lower bound on the other one is also 1.
Yeah.
Wouldn't you end up adding the infinitesimal vertical line there at 1 twice?
I suppose, but it's infinitesimal. It feels like an infinitesimal. It's actually 0. Right. Right. It's not a problem. Yeah, exactly. But I get your concern. Yeah, got it. Okay, so try not to slice through corners for this reason. Unless you just, for whatever reason, I don't know, if you just like the idea of cranking out that instead of this, suit yourself. And I get, look, every so often there are some situations where maybe this would end up being 2, for whatever reason, easier integrals, maybe. And this might end up being, it's only 1, but maybe it's somehow much harder. There's examples of this kind of thing, but they're pretty rare. Most of the time, try to avoid the obvious doubling of the work. Okay. All right. I'm going to go pretty quickly through this next couple of pages because a lot of this stuff is pretty straightforward. You'll notice that these first 3 properties of double integrals are, they look just like properties of single variable integrals. Right? They're pretty natural. No surprises, I hope. So just make sure to read that. Make sure that you're aware of these facts. A couple more that are pretty believable. The one that I'm going to talk about that I think is least obvious, I'll say, is this one here. If you do a double integral with an integrand of 1, that will give you the area of the domain over which you're doing that integral. There's a couple different ways to see that. I don't know why. I used to think it was most easy to see because if the integrand is 1, I had this urge, as I think a lot of y'all do, to think of the integrand is height. I could not pull myself away from thinking of the integrand that's the f of x comma y that is your z, that is the graph that you're finding the volume under. Because, as most people do, I started off thinking of integrals most fundamentally as being geometric, which, again, I'm trying to wean you all away from. But, along those lines, what volume would you get if the height is a constant 1? Well, you'd have area times height. The height is 1, so the volume would be the area. So, pretty natural, right? Now, here's an even easier argument than that. Keep in mind what an integral really is. Forget about volumes. But that's an application that's convenient in some cases, but most fundamentally, this is a Riemann sum. This says I'm taking this domain, I'm chopping it up into teeny tiny little pieces, and for each of those pieces of area, I'm going to take the area of that piece. I'm not going to do a thing to it. I'm going to multiply it by 1. That does nothing. Right? I'm going to take those areas and I'm going to add them up. Well, of course, that gives you the total area. Right? If you take a region, you chop it into little pieces and add up the areas of all the little pieces, of course you get the area of the whole thing. So it's actually easier to think about this fact from a point of view of Riemann sums. Okay. And this little asterisk, I had this urge to put this in there. It turns out there are some regions that are particularly nasty where area isn't defined. But this is not at all Math 212 appropriate. I kind of regret putting that in there, to be totally honest. But if you're curious about what would a region look like that doesn't have an area, it takes a little bit of doing to explain it, but come to my office hours and I'll show you. Yeah.
It's 2, then is it 2 times the area of 2?
Yep. Mm-hmm. Yep. Because that 2 would just factor right out like so. Yep. Okay, so there's a couple of examples in here, and I'm going to let you guys read these examples going down to page 104. They read pretty straightforward, and we'll pick up there next time. So a quick announcement. So I mentioned last time that I was contemplating doing a catch-up recording day. So I'm going to do that. There's a set of topics that we're coming up very close to that I think is sort of the perfect topic to do something of that sort. So it's going to be some physics applications. And it's just a bunch of formulas that you have to, know the formulas, and then ultimately you're just kind of applying the ideas that we've just been talking about. So I'm going to send you all an email about that. The chronology is going to be that you're not ready to watch that video quite just yet. So on Wednesday, today's Monday, right? Yeah, so on Wednesday, I'm going to lecture for a certain number of pages, and then I'm going to skip several pages of those physics applications and say, y'all can view the recording on this later, and then I'll proceed from there. And then y'all can fill in those blanks subsequently. And I'll send you the recording. I'll send you a link to the recording anyway, and detailed instructions. Okay. See y'all later.